Recording is live. Okay, I apologize for that. I'll restart the sentence. Molarity is defined as the amount of stuff, and this stuff is commonly just referred to as solute, present in a solution. It's the amount of stuff, and that stuff word used right there is meant to be as broadly descriptive as possible. To better understand what I mean by stuff, let's think of something like lemonade. In the case of lemonade, we have two things. We have the solution, which is, of course, our liquid water. That's our liquid medium in which everything takes place. And then we have our solutes, our stuff, where in the case of lemonade, we have both lemon juice and sugar. Now, lemonade gets this point across very well because it's something we understand the basic principle of. You can add a solid, such as sugar crystals. You can add another liquid, such as lemon juice, to the water. You won't necessarily see the sugar crystals, but you know it's there. The lemon juice, you'll recognize it in that pale yellow that we know too much about lemonade. What I'm trying to say is we know the stuff exists in solution. We may not see it, but we know it exists there. In the case of lemonade, there are two things that can happen. Give me a second just to draw the arrows. Whoops. To a cup of, oh, that's really bright. Let me actually change the color of that. Yeah, that looks more, yeah, that's at least a better contrast. We can do one of two things to a cup of lemonade. Traditionally, we can either add more solution, we can add more water to our cup of lemonade, or we can add more solute, more stuff, aka we can add more lemon juice and sugar. In the case where we add more water, one of the things that we do expect to see/know/taste is that the lemonade becomes slightly more watery. That's what you describe it as. Maybe you say thin. I know me, spoiler alert, I like Indian food, or as I like to call it, food. Mango lassi is a litmus test for me. Some of them are like thick smoothie milkshakes that I love. Some of them are not. What do I describe them as? That mango lassi is really watery. Why? Because there's a lot of water. There's a lot of solution. The chemical term used to describe this is dilute, aka go dilute the bleach. Go dilute the cleaning solution. When we say dilute, what do we literally mean in conversation? Go add some water to it. Dilute the alcohol. Cut water. That's pretty much all it is. That's one situation. We can add more solution, more water. That's called diluting. And of course, in the other case, where we add more lemon juice, more sugar, what do we call that typically? We say that the lemonade has now gotten too bitter or maybe too tart. There's too much stuff in it. The term we use to describe this is concentrated. This, of course, may also be intuitive to us. If you've ever shopped at any grocery store, I'm thinking of Trader Joe's, you know they sell gallons of fruit concentrate. Cartons of juices that when you taste it, you can say, oh yeah, that's definitely mango juice. That's definitely apple juice. Some people like the tartness. These two terms help us understand what we're talking about when we talk about molarity. It's the amount of stuff in relation to each other. If there is a lot of water, it's dilute. If there is a lot of stuff, it's concentrated. What this tells us is that to measure molarity, it is quite literally a ratio of the amount of solute, aka stuff, in solution. It's a ratio. If you have a lot of solute, it's concentrated. If you have a lot of solution, it's dilute. The amount of stuff is in the units of moles. That's our chemical currency, everything that we can use to understand and quantify reactions in chemicals, moles. And in the case of solutions, which is a liquid, that's in terms of liters, a capital L. Now, some resources between online or in your textbook prefer to convert the liters to milliliters, which would be 1,000 milliliters. Do note they mean the same thing. 1 liter is 1,000 milliliters. They're interchangeable, just depends on the person who's writing the text. They have their preferences. The unit of molarity is a capital M. Now, I just want to point something out right here. My handwriting is such that my lowercase m and my uppercase m do look alike. So sometimes it can be confusing if I'm writing a capital M. So when writing, I'm going to explicitly put lines under the M to make it abundantly visually clear we're talking about molarity. On a typed worksheet, you will be able to clearly tell if an M is capitalized. So just to reiterate, when writing, I'm going to put these lines under my M to make it clear we're talking about molarity, but on a typed printed worksheet, we'll use a capital M. Okay, this is molarity. It is a unit that's used to ultimately measure the concentration of a solution, whether it's highly concentrated or not, aka dilute. It is a measure of how much stuff is in solution. Now we have somewhat of an equation. We can say that molarity is equal to N, which we know is our unit for number of moles, divided by volume, V. N is moles, V is volume, which, remember, just depending on the context, could either be in liters or milliliters. You are expected to know that the conversion between liters and milliliters is 1,000 mils. Now, this formula represents an addition to our arsenal. From an earlier class, in fact, just a few weeks ago, we had devised a couple of formulas about mass and moles. We had N is equal to M over MM. We just did that. A couple questions like that on the board. In other words, we knew how to convert, whoops, not hot, between moles and mass. We used the formula, which included molar mass. With today's formula, M is equal to N over V. This can actually be a quick move around, a quick rearrangement to say N is equal to molarity times V. Notice all I did there was just cross multiply. With this new equation, we can now convert between moles and volume. We can convert between mass to moles. That bus pass is molar mass. The formula is N is equal to M over MM. And now we've learned the newest one. Moles can be interconverted to volume using molarity. where the formula is N is equal to M times V. I would like to introduce the new roadmap. Take a second to look it over. I do have printed handouts I'm about to hand out. Take a second and look it over. Understand where everything is. Take one and pass it down. 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 This is the new and latest roadmap. As we look through the image on the projector, as you all get a copy of the handout, I want you to take a second or two to really look it over and understand what we're looking at. On the top half, we have mass. In the middle, we have moles. That top half should be one we're accustomed to. We are now adding the bottom half, converting between moles to volume. And the bus path we use is molarity. And the formula we use is capital M. Now, this is what I meant by on printed worksheets. You'll be able to clearly tell if the M is capitalized. But when I'm handwriting, I'm going to put a line under it. Take a second to mull it over. Yeah.
That's it, nothing else.
It only goes through moles, not molarity. It's between these two specifically. Good question. Remember that mole ratio stoichiometry is all about connecting moles. That's our connection between the two sides. Another handout coming your way. Yes. Yeah. Everyone should have a copy of the handout in front of them right now, so I can quickly go back. Take one and pass it down. 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 Another handout is coming your way. It is today's in-class problem set. We all know how this works. We're going to go through a couple questions together for practice. Tomorrow's lab is a wet lab. It's a pretty short one. Part of the wet lab actually has you doing a worksheet. So you're going to get additional practice on this topic tomorrow as well. So for today, we're going to do some questions together. I got it. Which table needs any extras? So this table is all out. Okay. 1, 2, 3. Riley, did you get one? No.
Thank you.
Yeah. Is there anyone who's missing a copy? Okay, 2 handouts. One of them should be the roadmap, and the other one should be today's in-class problem set. Here's your extra credit. Any 5 questions. Notice that some questions have parts. The extra credit for today's worksheet, today's problem set is any 5 questions. As a topic, molarity is pretty light. We're actually done teaching molarity for today. It's just a new concept that we've introduced that we're adding to our repertoire of the roadmap. So to better understand what molarity is, how to use it, how to exploit it, and how it helps us in the roadmap, let's do a couple questions. I'd like to start with number 1. Everyone has a copy of the roadmap in front of them. Here's my promise to you. This roadmap This PDF, this image will be part of your exam. It will be provided to you. You do not need to memorize the roadmap. Just like the solubility table, just like the periodic table, a copy of the roadmap will be part of the exam booklet. So I don't need you to memorize it. What I need you to do is learn how to use it. Let's start with number one. I'm just going to copy this over on another page so I have space. Okay. Very first question asks, how many grams of calcium carbonate are needed to make 725 mils of a 1.7 molar solution? In this case, we are being asked information about one chemical and given information about that chemical. So the first part, A, is not a roadmap. We are not connecting two chemicals. It's just the one. We can see that in the part A, we're being asked to find the mass. We are told the volume is 725 milliliters, which when needed, we will convert to 0.725 liters. We are told that the molarity is 1.7. This is not a roadmap. This is just asking you to identify what equation and what to plug and chug. So we know, since we're being asked about grams, mass is equal to number of moles times molar mass. That's an equation we've already known and established. What we know from today's lecture is that N is also equal to molarity times volume. So we're going to put it all together and say that mass is equal to molarity times volume times the molar mass. This is taking an equation we've established and used before and integrating it with our newly taught topic from today. We're trying to find the mass. We know the molarity. We know the volume. Only thing we need is to know the molar mass. The molar mass of calcium carbonate is equal to the sum of calcium plus carbon plus 3 oxygens. This is approximately 100 grams. Yeah, Paul. Good question. This is not a roadmap connecting chemicals. So do we need to balance it specifically for A? No. If you did balance it, it will probably help you in the future. But for part A, it is not needed because it's not a roadmap question. Thank you for asking that, Paul. It's a very good clarification. Balancing will absolutely help us in the long run, but it's not needed for part A. Part A is only asking about one chemical. Putting it all together, we get 1.7 times 0.725 times the molar mass. If I put this into my calculator, 1.7 times 0.725 times 100, I get approximately 123.25 grams. That right there is our final answer to A. Please note that I did convert the volume to liters. Like I said, we will be using liters, but some resources or textbooks online might use milliliters. We will be sticking to liters. So it's on you to recognize when you have to convert or if you have to convert. I see a hand from Aletha.
So 100 grams from, we know that it's from like 100 grams that you got.
So it is from the sum of the individual elements calcium is 40 grams, carbon is 12 grams, and 3 oxygens is 3 times 16. If we add this all up, we get 40 plus 12 plus 48. In total, that's approximately 100 grams.
That's from the periodic table, right?
Yes.
Oh, okay.
Any other questions on part A? Yeah, Alexia. This one up here on the board? Okay. Any other questions? Yeah. Tight.
Get that M2 on the top. Next to A. The first thing you write is M. So
Oh, that's a question mark. I apologize. Let me just make that a little bit clearer. That is supposed to be a question mark. Any other questions on A? Okay. Now let's do part B. I'm just going to move this out of the way so it's not well, it's not in the way at least. Part B reads, how many mils, okay, so ml, so eventually we will need to convert. How many mils of HCl is needed to completely react with 56.1 grams of calcium carbonate? Analyze the question. You are being asked information about one chemical and given information about another chemical. This tells us we will be using the roadmap to connect HCl and calcium carbonate. Let's go ahead and now draw our new roadmap of 3 boxes on both sides, where the 3 boxes are from top to bottom: mass, moles, volume. Our individual bus passes, we have molar mass on top, and we have molarity on the bottom. And the connection is between the moles, and that is, of course, the ratio. I have simply drawn the roadmap. I have not started filling it in. I see your hand. I'll get to your hand in a second. Remember, you do not need to memorize the roadmap, but it will be provided to you. So knowing how to use it is more important. I saw a hand in the front. Yeah. No, sometimes I could ask you to calculate molarity. Yeah. The roadmap tells you everything that you need to calculate and do. That's a good question. I'll try to do one of those questions after this. So the question is asking how many mils of the HCl. It's on us to know that mils is a measure of volume, milliliters. So we're being asked to find this guy down here. Actually, I'm using another color for some contrast. Down here, we're told that the molarity is 3 molar. Okay, so let's just update that. 3m. And we're told that we needed to react with 56.1 grams of calcium carbonate. The roadmap points the way: moles to mass, mole ratio, moles to volume. It is the same principles we've always done with the roadmap. We've just added a new stop. Based on this direction, we can very comfortably say we do not need some of these boxes. They're not on our way to our answer. It is not helpful to have them. Let's just remove them to clear it up. All that's left is to fill in the molar mass. We have the molar mass from the previous question. That was approximately 100 grams. And now we need to fill in the ratio. All right, so now Paul's question becomes relevant. Now we need to balance the equation. Looking at it from left to right: 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygens, in total 3 oxygens, 1 hydrogen, 2 hydrogens. So quickly balance that. We'll put a 2 in front of the HCl. 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. The reaction is now balanced, and we can clearly see the ratio between calcium carbonate and HCl is a 2-to-1 ratio. Did I put this in the correct order? Yeah, I did. There is a 2 in front of the HCl and a 1 in front of the calcium carbonate. So it's 2 to 1, not 1 to 2. The roadmap is now filled out. Let's plug in everything and solve it. Very first thing we're going to try to solve is mass to moles for calcium carbonate. We know the formula. Number of moles is equal to mass over molar mass. That's 56.1 divided by 100. I'm going to put this into my calculator over here. 56.1 divided by 100 is approximately 0.561. I write that into my ratio table, my roadmap, just to keep track of stuff. Oh, that shouldn't be grams. Sorry, that should just be 0.561. All right, we do have here a nice, convenient 1 to 2 ratio. The 1 to 2 ratio means just to multiply it by 2. That's what 1 to 2 means, quite literally. So we can very quickly multiply our answer by 2 to get 1.122. Lastly, to go from moles to volume, specifically for the HCl, our new formula is N is equal to molarity times volume. So to get volume alone, we divide both sides by molarity. Volume will be equal to number of moles over molarity. This is equal to 1.122 divided by the molarity of 3. Oops. That number divided by 3 is approximately 0.374. All right, trick question. Are we done? No. Why aren't we done? Because the answer is in, thank you for that, is in liters. The question specifically asked for milliliters. To convert to milliliters, we multiply by 1,000. This becomes 374 milliliters. That's question 1. Do we have any questions on any part of question 1? Okay. Just a reminder, your extra credit for this problem set is any 5 questions. Let's do another one. Let me pick one. It's 12:30. Okay, let's do, no, that's a bit too big. Let's try this. Yeah, let's do number 4. Tomorrow's lab is a wet lab, but part of the wet lab worksheet has you doing a couple practice questions, so you will get your own practice tomorrow. Let's focus on trying to get through some guided problems together. Yes? Don't forget that these lectures are recorded, so you can always just refer to the YouTube video afterwards. But I do get it. Sometimes it's more convenient to take a picture in the moment. I used to do that too. All right, number 4. Just to kind of prove what I was saying earlier, let's just go ahead and immediately try to balance this equation. We don't know if we need it just yet, but there's nothing wrong with balancing it straight off the bat. 1 sodium, 1 sodium. 1 OH. Okay, well, technically there is no explicit OH over here, but it's on us to remember that H2O is identical to HOH. So 1 OH on the left, 1 OH on the right. 1 hydrogen, 1 hydrogen. 1 Cl, 1 Cl. So the equation is balanced as written. Let's focus on part A first. The question says, how many grams of sodium hydroxide are required to react with 500 mils of HCl? This is a situation where we are being asked to find information about one chemical after being given information about another chemical. So roadmap will be used. We are connecting sodium hydroxide and HCl. It's going to take me a second just to draw the roadmap myself. I should copy paste it. Molar mass. Molar mass. Oh, whoops. That's not the bottom half. Whoops. To molarity. And then between the two is ratio, mass, moles, volume, mass, moles, volume. And I'll just copy this immediately so I don't have to keep reusing it. Ah! Oh, thank God. Okay. Filling in the information we're being asked for and what we know, we're being asked to find the number of grams of sodium hydroxide. We're told we're dealing with 500 mils of HCl. Let's immediately convert that to liters. So divided by 1,000 gives us 0.5 liters. Remember, we're going to work with liters. We're told that the molarity of the HCl is 1 molar. The path ahead becomes clear. Volume to moles, ratio, molar mass. Let's take a second to just clean it up so it's a lot clearer what we're going to use. We have the volume, we have the molarity. We will eventually calculate the moles. We need the ratio. We've already balanced the equation. We recognize it was 1 to 1, so the ratio is exactly 1 to 1. All that's left is the molar mass. The molar mass of sodium hydroxide is equal to the mass of sodium added to the mass of oxygen added to the mass of hydrogen. Sodium, when rounded, is 23 grams. Oxygen is 16. Hydrogen is 1 for a total of 40 grams. With that, we have filled it. Oops, I don't want to copy that part too. Okay, great. With that, we have filled in the roadmap to our best capabilities. We're going to ignore the question right now and do what the roadmap tells us. First things first is volume to moles. We know that our formula is N is equal to molarity times volume. We know the molarity is 1. We know the volume is 0.5. No calculator needed. This is just 0.5 moles. Immediately put it into our roadmap. I like to visually keep track of it. This is a 1-to-1 ratio, the simplest one out there. We can just immediately write that number back. Part 3 is going from moles to mass, specifically for the sodium hydroxide. Mass is equal to number of moles times molar mass. 0.5 times 20. Sorry, times 40. I'm just getting ahead of myself. Times 40. That is approximately 20 grams. Do not let the new roadmap scare you. We have just added a new branch to it. The process is the same. The formulae are different, sure, but the process is the same. So don't worry if you didn't have a good handle on it for the last exam. You're going to get more practice. This is now the point where I can tell you that your next exam will be entirely multiple choice. Don't know how many questions just yet, but entirely multiple choice. I did notice that Tuesday's exam ran long, so it tells me that that was too long of an exam. So I think switching it up to multiple choice is a smarter idea overall. I don't know how many questions just yet, but it'll be multiple choice. Any questions on part A before I move on? I see a hand. I can't hear you. Sorry, Serenity. Yes, the question told us that it was 500 mils. We're going to be working with volume with liters, so we had to convert it to liters, which is divided by 1,000. Any other questions on part A? Okay. Moving on to part B. Just going to move part A out of the way so I have space. Yeah. Never mind. Okay. All right, so A is out of the way. Next up is B. Question being asked is, what volume of HCl is needed to react with 40 grams of sodium hydroxide? Okay, so we're being asked information about one chemical after being given information about another chemical. We're going to do another roadmap, again, between HCl and NaOH. This time we're being asked the volume of HCl. Whoops, wrong side. We're told that the molarity of HCl is 0.5. We're told we're dealing with 40 grams of sodium hydroxide. The path ahead is clear. Mass to moles, mole ratio, moles to volume. Tidying it up so we can just increase clarity. We need a couple things. Fortunately, we just did this roadmap very similarly. So we already have some of the information. The molar mass is 40 grams. The ratio is 1:1. Now we're going to solve it. First things first is mass to moles, specifically for the sodium hydroxide. That's our very first step. Number of moles is equal to mass divided by molar mass. No calculator needed. This is just 1. The mass is 40 and the molar mass is 40. 1 mole. 1:1 ratio tells us 1 mole. And to go from moles to volume specifically for the HCl, we're not used to the formula just yet, so let's spend some time. N is equal to molarity times volume. If we want to get volume alone, we divide both sides by molarity. We get 1 divided by 0.5. This is 2. What unit is this in? Liters. Do we have any need to convert it? No, because the question simply said what volume. It did not specify liters or milliliters. It just said what volume. So we got it in 2 liters. So the answer is 2 liters. We're working with questions with fairly straightforward numbers to kind of demystify the math section of it all. Any questions on B before I do the last one, part C? Okay. It looks like I'm mostly out of space on this page. Let me just make a new one. And we're doing B. We're moving on to C. The question reads, how many grams of water will form from 72.5 milliliters of a 0.17 solution of sodium hydroxide? To no one's surprise, we are yet again doing a roadmap. Comparing HCl and NaOH, There are a lot of stuff that we can fill in. Question is asking how many grams of water. Oh, it's actually asking water this time. Look at that. So it's not the exact same. H2O. And sodium hydroxide? Yes, it is sodium hydroxide. Great. How many grams of H2O will form from 72.5 milliliters? Okay. We don't like working with milliliters. We're going to divide by 1,000. This becomes 0.0725 liters. 0.0725 liters. And we're told that the molarity of this solution is 0.17. Roadmap is clear. Volumes to moles, mole ratio, moles to mass. The only thing we need is the molar mass. Quickly calculate that. The molar mass of H2O is equal to 2 hydrogens plus the oxygen. 2 plus 16 gives us 18 grams. Erase some of the unnecessary bits. All that's left is the ratio. We've already balanced the equation, 1 to 1. Same process as always. Very first step is volume to moles, specifically for the NaOH. Number of moles is equal to the molarity times the volume. That's 0.17 multiplied by 0.0725. Putting this into the calculator, 0.17 multiplied by 0.0725. We get 0.0123. We write that in. Upon recognizing that the ratio is 1 to 1, yet again, we can make the very simple conclusion that it's the same number, 0.0123. All that's left, of course, is moles to mass, specifically for the water. Mass is equal to number of moles times molar mass. That's equal to 0.0123 multiplied by 18. Times 18 is equal to 0.22185, which I will just round up to 0.222 grams. So as daunting as a new roadmap might be, it is simply deepening our understanding of stoichiometry. Now that we've introduced the concept of molarity, aka concentration, we now have a way to relate mass to volume very simply, just by use of formulae. Tomorrow's lab will be focused on stoichiometry and molarity. There's a wet lab portion, there's a small dry lab portion. And next week, we'll start a new topic called acids and bases. That's it for today. If you have any questions, come talk to me after class. If not, we're good. What was your question?
I was going to ask, where are you supposed to find the molarity?
So let me pause the